Hello, we'll give people a minute to get here and for me to stop coughing, and then we'll start. Hmm. Hmm. Wow. So we have 100 subscriber points on Twitch, which means you could have 9 emotes. I'm sure that would elevate the quality of discussion. If we had 9 emotes. Dude, we got another Twitch subscriber. Let me refresh the private lounge. All right, we'll give it about 1 more minute and then we'll begin. 1 more minute. Oh, it's, hey man. All right, what are we doing today, you may ask? Whoops, I'm in the wrong window. And I may answer, I'm trying to improve the quality of the animation system, and there are some problems. So right here, we're just playing an animation of a character rotating, and there's about 15 keyframes around the circle. And you'll notice that his arms are kind of stretching out and contracting, which they're not supposed to be, I'm pretty sure. Unless that bug is in the original animation data, which I sure hope it's not. Actually, I know it's not. So that number that I'm printing out there it's the fraction of the next keyframe that we're interpolating, right? So we have some number of keyframes in the animation, and so when we're exactly on one keyframe, then this is 0.000, and as we go between that keyframe and the next one, this number goes toward 1. And what you'll see, I mean, it's probably hard to see. We could slow this down a little more, but then it's maybe hard to see when the arms are longest if we really slow it down. But what you'll see is, like, you can sort of see the pop at the end when the arms are longest. And if you look at the number right there, it's hard to look at both at the same time, but you'll always see that's when the number is 0. So what's happening is our keyframe interpolation is shrinking the bones a little bit, which I guess means maybe there's a numerical accuracy problem. And the thing is, we're doing lots of stuff, so I'm maybe not that surprised, but first we're going to look at the situation, and then we're going to try and determine where the accuracy problem is. Having accuracy build up so much that it's this visible is unusual unless you just really made a mistake or did something wrong. So there's that. Like, these are definitely, the arms are definitely leaf bones that are like many things down, but you can see, you know, usually like the root is right around that point in the middle where all the lines are coming out or near there. So I don't know how many bones it is from there to the arm, but it shouldn't be so many that it's a disaster. But yeah, there's all sorts of things we could do if we fear numerical accuracy problems. We could like do math in doubles or something. Anyway, let's just refresh our memory of like what all happens, because I vaguely know what all happens because I wrote this, but I don't totally know what all happens. It might be hard to see the stretching. Let me speed it up again. And let me turn this off so there's less. If you just look at the arms, you should be able to see them bobbing in and out. It's probably, like, I'm looking at this at 60 FPS right now, and you're probably seeing it at 30 or something. I don't know. So here is where I think it's the most visible. It's just hard to watch the number at this speed. All those cyan lines are bones. Yes, they are. Now, the way that I know, I don't have a runtime switch for this, but I have a compile time switch. The way that I know that it is, I mean, besides just looking at the number, we can do the following thing. We can go to Sokoban source animation player, and there's a disable lerps here. If I turn this on, then we won't ever interpolate between frames, which means everything's going to be really jumpy. Whoops. Well, let me show you what that looks like here. Whoa. That's kind of crazy. Well, in this case, not interpolating between frames is well. Highly questionable. There may be some other bugs happening. We have this, the reason I'm debugging rotation is that we have weirdness happening when it comes to the guy turning around has some compensation for the game's turning built in. And that's like not being interpolated while we do this, so it's weird. But like you see here, there are not that many keyframes, right? Anyway. So factoring that out for a minute. So here's sort of the T-pose thing. That time you saw blending because we were like, that wasn't keyframe interpolation, that was like blend interpolation, which this variable doesn't turn off. But here, there we go. So that was, again, some animation interpolation blending in, but now that's done. And so what you see is we're just playing back each keyframe. Of course, because it's teleporty movement, it would be hard to see any stretching or anything, but it doesn't look to me like any is happening. But this gives you an idea how far the keyframes are from each other. So now what happens is when we hit 0, he just goes to the next keyframe, and that's that. Am I looking for a bug in the interpolation or the rendering of the scene? The interpolation of the bones is what's wrong here. It's not going to be a rendering bug. I don't think. If it were a rendering bug, that would be really weird. It could be anything, honestly, but the fact that it really only happens at keyframes means it's very overwhelmingly likely an animation bug. All right, so so here this is sort of the loop that interpolates between frames. We have this thing called getXFormState, and XFormState is a struct. We can go look at that for a second. That is in sample animation. So it's just very simple. It's got the state of that node factored into a translation, an orientation, and a scale, right? So eventually we multiply these things together to get a matrix. But in the meantime, we don't. So basically, if we're disabling lerps, right? So, we call this routine and we say, here's the current time. And then we figure out what that time means in terms of the index of the base sample and then the fraction, right? So the base sample gets put in index, right? And then the fraction is this float 64. So we're even doing the fraction in double precision, which may not be necessary, but that's what we have. So if we're disabling lerps, then we ignore that fraction and we just grab state index. Otherwise, we get the state for index and the state for index plus 1. And we do a lerp between those. And we have a lerp defined. I don't know if that's here or... Yeah, it's here. So we just lerp the translations. We slurp the quaternions. Normally, I use nlerp, normalized lerp for quaternions. But just for avoidance of doubt, I'm I moved this to slurp for now. And then we lerp the scales, which are vector 3s. So in principle, this should be totally reasonable. Now, I suspect, like, float precision should be totally fine for all of these interpolations. Here's what I suspect is the problem, if I'm being honest. We're just doing too much math on stuff. So anyway, this guy who does this is the channel, right? And then it's the animation player's job to mix all those channels together, like if multiple animations are playing and stuff. And we do a bunch of things for that. All of this animation code, by the way, is ported from the witness, which is a later version of stuff that I wrote earlier. So when we tell the animation player to figure out the current state of the animation, it goes over all the channels where each of these channels is possibly playing back an animation like walking or running, and then we want to blend between them. Or some of them could be IK channels, which we have turned off in this game, but you could have that, right? If there's no change, we just return. Otherwise, then we say, let's go over all the channels and we compute the state relative to the parent. Oh, the channel already did that. And then we interpolate in these relative to parent spaces so that most interpolations are small. Right? So this lerp is on X-form states. And then we blend in the relative to parent space. And then we switch back eventually. Anyway, so we have these relative to parent situations. We blend all those together. Then we've got to go back to non-local transforms, because that's what we use to render. So, we get for every node in the hierarchy, right, for every bone, we get the matrix for the parent. We get the matrix for this. We multiply the matrices, and then we set a new X-form state from that matrix. This is a bunch of spammy math that is not really necessary and probably inaccurate. And the reason is, like, our outputs here used to be a matrix, but now it's one of these X-form states. And so, we could do the math on the X-form states directly. I would have to figure that out. But this is kind of sloppy. This is probably generating a lot of error. And it's also slow. Right, so we said speed, we could concatenate X-form states directly. So part of this stream might just be me figuring out the math to replace this. In fact, that would be a good place to start. Because we don't want to be paying the speed cost, assuming that this is really the way that we want to do it. Anyway, so at the end of this, we have the state no longer relative to the parent, but we have the, the parent state times our state, right? So this comment is basically redundant to this comment. So let's just make that one easier to see and remove that one. Okay. So then maybe we remove the locomotion from the root bone or not, depending on what we want to do. And then we actually generate the output matrices from these X-form states, which like actually, so for this subtraction, like, why don't we remove locomotion while everything is still relative, dummy? I feel like I tried this and it didn't work, but we should try again. Okay. Anyway. So because we're not doing this early, everybody has the translation added in because we just transformed, we put all the parent on, and so we have to like do the translation correction to everybody. That's fine. Oh, I guess it's the z coordinate thing. Yeah, it would take a little bit more to compute this correctly, but we could. Okay. Then we compute the output matrices as 4x4 matrices, which is what rendering wants. So here, one thing we could do is just stash this matrix and use it again, except that we would have to do this locomotion on the it's not worth it. So I think what we want to do is let's think about the math here and just do it, right? Okay, so what format do I use for animation files? I tried using Collada in my engine. It's just a huge generic format. We do not use a very efficient format right now. We just have our own text file format. It's not super fast, and the more animation we have, the sooner we will have to switch off it. But it's a lot faster than Collada. You're casting to float in the call to lerp. Is there a chance you're dropping precision at that point? Well, we shouldn't need that much precision. Like a floating point number between 0 and 1 has, 23 bits of mantissa. So that should be accurate to the power of 2 to the minus 23. Because we don't need any bits greater than 1. You know what I'm saying? That should be plenty of precision. You shouldn't see 2 to the minus 23, right? The implementation of lerp could potentially have some other problem with being done in single precision, but the parameter being single precision is not the problem there. IK is inverse kinematics, yes. Okay, so you could think of the transform state as a translation, right? A rotation, which I'm going to call Q for quaternion because that's what I'm used to, and a scale, right? It's these three things: translation, rotation, and scale. Let's write that down. I could write R, but I just think of it as Q all the time. So Okay, translating a vector. You just add t to the vector. Scaling a vector, you just say s dot x times v dot x, s dot y times v dot y, s dot z times v dot z. But of course it matters whether this scale is supposed to be applied before or after the rotation, because the rotation will change the axes of the scale. I don't honestly remember. I think it's probably before, but we'll take a look. And then rotating a vector is q times v times q star. We can just write that as, let's write that. So that's a complex number multiplication, though, and it's maybe not the easiest way to think about it if you're not used to it. So maybe we don't expand that if we do the algebra, right? So basically we want to compose these, right? So we have a parent state and we have our state, and we basically want to say if we have t child, q child, s child, and t parent, q parent, s parent, right? Then we want to compute, well, let's pick an order. Let's say the order is t, q, s, v, right? Where each of these is a transform. You want to, see, here q is a vector, a 4 vector. Here, let's just say it's a transformation matrix, right? So if we, and this is like column vectors, so it's scale and then rotate and then translate, right? So if that's the order of operation, then we want TP, QP, SP, TC, QC, SC, V, right? Because we translate it by the child stuff and then translate it by the parent stuff. And then if you mash all of these into, I don't know, let's call them, I would say C for combined, but we already said C for child. For so both, B for both, we want that. We want to find this equals TB, QB, SB, V, right? And then this is what we store in this state, as opposed to, you know, doing a bunch of going to matrix and back because we're lazy. You dig? And the other reason to have this as a transform state and not a matrix is that it'll be easier to draw on the screen in debugging tools. It's like easier to understand. A 4x4 matrix is really hard to look at and like know what the hell's going on. Good morning. Welcome, Parker Johnson. So does anyone have questions about this while I go and verify the order of these operations? Get matrix. Really? Where is it? It's in channel. These things are spread all over the place. Oh my God. So I just expanded this out and didn't really write down what the order of operations is. Okay, it's clearly translation last. but it's maybe scale first. It's maybe scale first because otherwise these would be rotated. So we're computing them in the opposite order here, but I think that's just so that we have a matrix to pile stuff into. Right? Otherwise, if it weren't scale first, if it were rotation first, we'd be rotating the scale vector and then applying it. If you scale the blue dude's transform, did that exaggerate the animation bug? It would just scale it the same way it scales everything else. Like, you wouldn't see a proportional exaggeration, or you wouldn't see a disproportional exaggeration. It would just be what you see when you scale it up. Okay. So well, okay, I'm going to write capital letter for the transform and lowercase letter for the vector version. So these are all lowercase because these are vector operations. Okay, so if we want to combine this, then we either have to migrate all these terms left or we migrate these terms right. I want to migrate these left. So we want TP plus QPSP TC. That's lowercase. We'll separate it. This is saying, hey, if we're going to translate, then we rotate the translation and scale by the parent stuff. Oh, that's actually not right. Is it? Is it? Oh, is it inverse? I never remember. I haven't done this in so long. I haven't done this in so long. Nope, nope, this is right. So if I do this, if I pre-scale and rotate this, then that'll give me this translation factor, right? So let's just say we're going to keep writing terms here. We're going to say this is equal to this times QP, SP, QC, SC, V. All right? You get me? You feel me? So all I did was I pulled this TC and dragged it to the left. I never do this kind of math typing into a computer, so I might make grievous mistakes just from like typing in ASCII here, right? So now we want to drag the scale across. So we're going to use star for like Hadamard product here or something. Okay, I want to put these scale terms together first, and then we'll shift them both left of the rotation. But so SP times QC SC, right? And then QP of this, all right? Actually, we wanted to drag the scales the other direction, if I'm being honest. Let's go back to this. Because it's consistent, we want the scales on the right because that's the order of operations that we've established. So we want SP to go to the right. So we want QP, QC, SP, let's call QC inverse. That's a prime, whatever. It's going to be inverse here. QC in SP times SC. Right, that times this Hadamard product V. Okay, so that's what we want in principle. And then that gives us our new X-form state in non-matrix form, right? So then, because we have here the translations, the rotations, and the scales. Assuming this is the correct frickin' order of operations, which we could test empirically, could do some data science. Do I have to ban Hyper Newbie? What's going on? No. Related to the previous streams, someone suggested import X in a namespace. Yeah, that's fine. You mentioned once supporting something like c.lib for releasing closed source libraries. Yeah, that's another thing. I mean, that's just further ahead than what we're thinking about right now. What did the PNC subscripts mean? That's parent and child subscripts. So, yes. Yeah. So, that's all good. I really just have to make sure. Let's just go back to our, just right here where I print this, I'm just going to do a super stupid experiment where I'm going to say X-form state state translation is v3 1 0 0 state dot orientation equals wait, no, the scale is second. The scale is second, I think. Okay. So does that compile? Well, I'm not in C++, so there's that. So we make this X-form state. Okay. Now, I'm going to say get matrix and I'm going to say V like, does that compile? So many operator timeses. Operator times. Which one takes a matrix? Okay. Vector 4. Oh. Okay. So let's just print that every frame. So this has nothing to do with our animation. It's just, okay, X is 0, Y is 4, Z is 9, W is 1. Okay, so 0 by 4 by 9. Well, either we get that by, well, let's see. Let's say A is V dot X times scale state, S is state dot scale times S dot X. Right? So we're going to scale first and then rotate A by Q and then A plus equals state dot translation. So either that comes out the same or it doesn't. So that is not the same. So that's a scaling and then rotating and then translating. So instead, let's try rotating V by Q scaling and then translating. Yeah. So rotation is first in this scheme. I'm not sure that's a good idea, but it's what we have. So let's start this over because none of that was quite the right order. So we have, okay, wait. We rotate, then we scale, then we translate. So it's this order here. All right. Here. All right. So, well, let's move the translation again. This is just changes this, right? Emacs, stop it. So then we want this scale to go there. So this is just SP times QP SC QP QC, right? So now again, we have our rotates, we have our scales, and we have our translates. And so what I should be able to do is program it this way And then, you know, for every bone, I'm just going to print out the result that I get this way from the other way. And it should be kind of close, but probably more accurate. All right, so let's comment out this bonanza. And let's go to there. Have I come across NAND game? Is that NAND to Tetris? Yeah, I think that's a good thing for people to try. I never have tried it myself. I think you're correct with TQS order. Well, the order is arbitrary. There's no correct order, actually, right? The order is just whatever we decided on when we saved our format. You can factor things into any order that you want. There are potentially, you know, better or worse choices based on what might be more accurate or what might take less CPU or something. But I believe on the server side, we just literally, or on the export side from the tool, we just literally do like a decomp, a matrix decomp in Maya or something, or in Max. Thank you for making the best functional programming languages. Everyone knows they are the future. My Haskell professor said so, and he writes a whole 4 lines of functional code a day. Well, yeah. Yeah. Oh, NAND game is different from NAND to Tetris. Okay. You always hated this sort of thing so many times, you just gave up and threw orders around randomly till it worked. Well, I've done enough of that to know that it's better to know for sure. So, okay, here's what we do. Okay, here, we're just going to do all this BS. Oh, not there. Here. We're just going to do all this BS that we're already doing. But we're also going to do this. We're going to say TB is states relative to parent I plus, okay, let's just say P is states relative to parent I. We'll give things short names. Child is current, oh wait. Child is states relative to parent. Parent is current states parent index. Okay. All right. So TB, right, is the parent translation plus, well, I don't know. I don't usually define vector 3 times vector 3. Someone did. Ignacio did, probably. All right, so I'll allow us to use it. The reason I don't usually do this is because, hey, is that dot product? Is it cross product? Like, people overload crap all the time. This is what's called Hadamard product sometimes, I guess, which is it's just a component-wise multiply, which is what you usually want in shaders anyway. So now that it's 2018, I'm kind of okay with having this overload. Whereas, 10 years ago, I would have said, no, you don't have an overload for times because it's too messed up. All right, so that being the case, we'll say it's p.scale times rotate c.translation by p.orientation, right? Is that going to compile so far? Yep. Okay. So that's our translation overall. We could even just get both matrices to start with and print them out. So the scale for both is going to be the parent scale times rotate child scale parent orientation, right? And the orientation of both is going to be p dot orientation times c dot orientation. All right, so we're just going to do this so we can get the matrix. This is temporary. Test matrix, matrix 4, and then we're going to print matrix old matrix, my matrix, and new matrix, test matrix. And I think I have a print matrix program function. This is not C++. Okay, we're just going to printing that every frickin' frame for every, oh my God, it's going to be so slow. All right, here we're going. Here we're going. Let's just Control C it somewhere. Okay, these matrices are not at all the same. So I screwed something up real bad. But we can probably tell what that is if I just screwed up one thing, because instead of printing the matrices, we could say, because we made this state M, oh no, we made the state, so that should also be almost the same as X. So we could say print old state This is going to be a little harder to read because it's the native printing the native data structures, which is going to spam us. But if it's too hard, oh wait, old state, we need to dereference. We might make a print xform state if that'll help us. All right, so old state minus 0.06, 0.05, 828.103. That's the same as new state. See that? That's good. Okay, orientation 524891 minus 507, 277.543, 624.052. Scale is wrong. Old state scale 111, new state scale blah. So like, how is our scale so jacked? What did we do? And like, is it scale 111 for everything? In which case, it's probably not true. There's probably some bone where the scale is not 1. Although I don't know. Maybe I am wrong about the scale order and it really is the other. No, didn't we determine? Didn't we determine here that we have to rotate, scale, and then translate? Yes, we did. That's what gave us the same result. Drawing graphics involves a more automated method. Well, it depends on what you mean by more automated. What happens when everyone calls different operations product? Then you get the state of computers that we have today. That is what you get. Okay. how am I screwing up scale? How is my get matrix and set from matrix in different files? That's absurd. Yep. So maybe I need to, what happens if I just normalize it? I just want to try something just because it's bugging me. All right. Let's just comment this out for a second, because I want to know if it's a quaternion normalization problem. Just in the go. Let's set that right now. I just want to know if it's this quaternion normalization problem that it could be. Nope. Still happening. All right. So post-normalizing this quaternion doesn't really do anything, which is weird. Like that would have been my number one guess for what's the problem. But it might be converting back to matrix. I don't know. There's the more math you do, the more opportunity there is for precision problems. So we don't want to do as much math as we're doing, which is why I'm doing this. So now we're back to the question of why is my scale not correct? That's not the right buffer. That's not the right buffer. That's the right buffer. Okay. Like it totally worked for the translation. Oh, I'm dumb. Because this is a multiplicative factor, it doesn't go through the same way. right? So let's say you have a scale factor s times v, and you have some rotation q. Q of SV no. This is where I start sketching on a notebook to figure it out. Like you can just do the linear algebra to figure this out, right? And you could do it in 2D to make it simpler, right? So let's say our rotation in 2D is cosine theta, sine theta. Well, it's a, yeah, something like this, right? So for a 3x3 matrix, and the vector would be normally say like Vx, Vy, Vz, right? So like what happens when I multiply this matrix by this vector and then you write it out? Well, let's do that, right? So this gives you cosine theta, and let's just say, well, now let's just write it this way. Cosine theta Vx plus sine theta Vy, right? And then this is minus sine theta Vx plus cosine theta Vy, right? And then this is Vz because this is just a rotation in xy and doesn't affect the z, right? So now all we want to say to figure out the effect of this is, well, we're scaling this by some factor. Now, because these are multiplicative, you know, Sx, Vx stays stuck together, and Sy, Vy stays stuck together, right? That is not the same as rotating the scale, I'm sad to say, right? Because if you rotated the scale, you would get cosine theta Sx plus sine theta Vy, and then you would multiply that by this, and you get cosine squared plus sine squared. Yeah, like, okay. If you just did the scale, you'd get cosine theta Sx plus sine theta Sy times cosine theta Vx plus sine theta Vy. You get like cosine theta Sx, cosine theta Vx plus cosine theta Sx sine theta Vy, you know, etc. You'd get a 4-term thing. You would get cross terms. So what I did is obviously not right. And it's just been so many years since the last time that I've done this, I don't remember offhand what is the right answer. I'm not sure. I think it's like you rotate by the conjugate of the thing. That's always the answer. It's always either like rotate by the thing or rotate by the conjugate of the thing. Let's watch Casey's intro to quaternions. Yeah. I am tempted to just try the conjugate. Just a little bit cynically, just to see if that's the right answer. And if it is, we'll justify it somehow. So I don't see why it would be, but let's try it. It doesn't look like it. Well, so much for our random stab in the dark. It's still not right. It's still not right. It's still not right. All right. So I mean, I know that you can factor these things in any order because they're matrices. They're linear transforms. So you can factor them back and forth. So well, we know this, actually. We know this. Okay, so if I have a scale, or yeah, this is easy, actually. So we have a situation where we have, it's easy if I am not an idiot. We have a situation where we have a rotation and a scale and a vector. And I want to change that into, let's use a prime. Prime here isn't going to mean inverse like I was. We want to turn this into a scale times the rotation times the vector, right? How do I do that? Well, to get the scale on the left, I have to, oh geez. Actually, let's not use, we're going to use prime for inverse, so let's say some other, right? Oh, so, well, you can say V equals S inverse Q inverse QSV, right? Because Q times Q inverse is identity and S times S inverse is identity, and that leaves you with V, right? So there's some algebraic trick you can play to do something here. Oh my God, it's been so long. I mean, you can definitely solve for one of these, and like you can say, I can do S0 to the minus 1 times QS, right, V. I'm just looking at this line above me right here, equals Q other V, right? So Q other is equal to S other minus 1 times QS, right? The question is, that's still more unknowns. Man, I wish I remembered this. It's so easy. Is it not just QO equals QS 0 equals S? Well, I'm not sure. Yeah, I would remember this much better if I did it more frequently. It's just literally, it's been so long. Applying S and then applying Q should have the same effect as applying Q and then applying S. If S is just scaling and Q is just a rotation. Yeah, that's what I think now. That's what I've been thinking for like 5 minutes. But like, I want to prove it to myself. And I guess the way to prove it to yourself is more like the following way. We're just going to do this. Q is this, right? For now, it's fine that it's a 2D rotation. S is going to be SX. I hope I get this in the right order, right? It's SX. Okay, we're multiplying by Vx, Vy, Vz, right? So Sx, 0, 0, right? So 0, Sy, 0. Right, because it's diagonal, okay, right, 0, 0, SC, right? So that's our scale, right? Because if you multiply this by Vx, Vy, Vz, you get, you know, Sx, Vx, Sy, Vy, Sc, Vz. And then if these indeed interchange, then you just multiply Qs and Sq, and you see that they're the same thing, right? So Qs is, well, I wish I had, there's some mode you can go into for Emacs to like, just be like, don't pay attention to carriage returns mode, but I don't remember what it is. We're not going to draw the matrix brackets, but whoops. Right. This is so much faster to do on a piece of paper. This may look like a tedious pain in the butt, but it's pretty fast if you just do it, you know. You just write it down. So you multiply this out, and, well, what do we get? We get cosine theta Sx, sine theta Sy, and 0. Gotta write these further apart. Right, is that right? Boom, boom, boom. And then we get minus sine theta Sx, cosine theta Sy, and 0, and Sc, right? Which sure looks like a rotation of a scaled vector to me, right? And then you just do it in the opposite order, and you convince yourself that the answer is the same, which you could just do in my head here, right? I mean, it's diagonal. There's a theorem that says that if it's diagonal, it doesn't matter in what order. But assuming I don't even remember that, and I'm paranoid and think I might be making it up, you can just do it in your head this way. So here, to get this, I was going rows by columns, right? Row by column, row by column, row by column. Here I can go row by column. That's Sx cosine theta, Sx sine theta, 0, minus sine theta Sx, wait, row by column, row by, oh wait, it's different. Hold on. Row times column is minus sine theta Sy minus cosine theta Sy. Right, so these are both Sx. These are both Sy. It's not the same answer. bro. Okay. SQ, let's see. What a mess, what a mess, what a mess, 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 what a mess, what a mess, what a mess, mess, mess. Okay. So that's so this is the way I usually do it, right? This is cosine theta. I should have just said C and S because most of this is useless characters. But cosine theta Sx sine theta Sx 0, right? Minus sine. I keep doing the wrong order. Okay. Minus sine theta Sy, cosine theta Sy, 0, and oh, but what? Yeah. Okay. And 0, 0, SC, right? So this is transposed. The Sx and the Sy are transposed here, right? I bonked my mic and now my keyboard sounds clearer than the voice. How's this? Is this better? I had it rotated. All right. Duotone says, I might be wrong, but if you have QSV equals QOV, then multiply both sides by S minus 1, Q minus 1. Right. Oh, yeah. That's the trick. Okay, let's go back to what I was doing there. Duotones reminded me of the trick. Okay, so you have Q and S, right? And you want to compute SOQOV, which equals QSV, right? This V is lowercase. So if you multiply both sides by S to the minus 1, Q to the minus 1, well, let's put this like this. So we're putting the QSV on this side to match what he typed, right? So we do that, and then I should know all this from Linear Algebra Done Right, man. That's such a good book. It's just been so long. So we do this, and then we multiply both sides by S to the minus 1, Q to the minus 1, right, times QSV equals S to the minus 1, Q to the minus 1, Q0, Q0, or QOV, right? So these annihilate each other, right? So you have V equals this, right? And what that must mean is that, this equals the identity times the vector, right? And so S minus 1, Q minus 1, SO, QO must be equal to the identity, right? So SO, QO equals, we can multiply by S on the left and then multiply by Q on the left. But we knew that. Or we kind of knew that. So what we want to know are the actual components of these, right? And the question is, can we do that without breaking these down into coordinates here? Actually, wait, this is just this restated, right? So I went backwards. I sort of went forward and then I went backwards, and now we just swapped these. So the question is there some intermediate result here that helps us at all? I don't really know that there is. I mean, the problem with this statement is it doesn't really say what S and Q are. So you can't really say a lot more about them. Like S and Q are arbitrary transforms. We haven't like added more information about that to this. Oh, right. So Maginor says diagonal matrices commute with each other, but not with non-diagonals. Yes, that is, yeah, I remember that now. I didn't remember it very clearly at the time. Okay. Well, so I think what we do is let's go back to this and let's put the full matrix here and because like it looks like, okay, we're going to get SX's in the column, SY's in this column, and SZ's here, which is the transpose of it's the transpose of a scaled thing. I don't know how that helps us. Let's I'm going to call this RXX RXY. Just to be a little more compact. So how do you get a scale out of this on the left? I don't really know. It has to like... You kind of just have to pick one. This is weird. This is more like a decomp operation. Because the thing is, okay, what value is this row scaled by? Well, you could pick an arbitrary number. I mean, it depends. But then, of course, your rotation will also be scaled, right? If it's not unit. So the determinant of the... something like that. Something, something. People are asking off-topic questions. When all scales in the axis of rotation are equal, you can commute them. Yeah. So it's possible. It's possible that that's actually true for the animations that we have here. But I don't know. Yeah, so the thing is, when we go all the way to matrix and then back here, we're like doing essentially a decomp operation that like decodes this by looking at the magnitude of whatever rotation you would get out of this and then saying the scale is the rest of the factor, right? If whatever I do here would not really be cheaper than that, then maybe I'm not going to save anything by trying to do this. I mean, it might be a little cheaper because we don't have to figure out the translation. I'm just going to look on the internet real fast. Swap order of rotation and scale transform. Oh boy, that is not really something you can search for. There's so much garbage information on the web about yeah, it's going to be so hard to search for this that I might as well not do it. What about a monoid? What was the reason we wanted to rewrite QS as SOQO? Because we're converting to this representation of orientation scale translation, right? And we want to do that without going to a matrix and back. And so we need to put the translations together and the scales together and the rotations together. Ray tracer guy raid. Okay, cool. You can watch me pathetically not remember my linear algebra enough to solve this. Like, I've done this exact thing before. I've done this exact thing. It's harder because I'm streaming. Like, it's hard to think while streaming, honestly. Could you do transpose SOQO MM? Dude, I can't read what you're trying to say because it's a bunch of numbers on one line. Yeah, maybe Corner Piece can tell me the answer to this. I have a scale and a rotation, and I want to turn it. I have a transform that's a rotation followed by a scale. No. Yes, I have a transform that's a rotation followed by a scale, and I want to turn it into a scale followed by a rotation so I can combine it with another transform. And just because I'm getting old and stupid, I can't remember how to do it. Maybe it's not actually that easy. If you factor it like that, you get a non-diagonal scaling matrix in the general case. I don't want to remove this. Okay, here's the exact problem statement, right? So I have this data structure that's basically translation, rotation, and scale, right? To be applied in a certain order on a vector. It's a slightly smaller and better numerically understandable thing than a 4x4 matrix, but then of course you can multiply these together into a 4x4 matrix anytime you want in order to transform things. So now I've got one of these for like a parent node and one for a child node, and I want to combine them. And the way I was doing it before, which is slow, is I was converting each into a matrix separately and multiplying the matrices together. So now what I'm trying to do is not do that. I'm trying to combine them directly. So if I have a translation, rotation, and scale for a child and translation, rotation, and scale for the parent, then combine them. And actually, it's really, if these are like right-handed column vectors, then the rotation happens first, and then the scale, and then the translation, right? So it's like that order. Yeah, this is all old. Down here, it's the right order. Anyway, so I think what someone just said is probably right, which is that in general, you don't get a 3x3 scale out when you do this, which means, or not 3, in general, you don't get a 3x1 scale out. You get a 3x3. And my representation doesn't have 3x3. So that's kind of the problem. If I widen up this representation to have a 3x3 scale, then I could do this, right? Because then it's trivial. Then, you know, in this product, you get scale factors, and then in this one, they're transposed, right? So you just transpose your scale 3 by 3. Wait. That's not right either, but anyway. The child's attributes are local to the parent, yes. So we're essentially just multiplying the two matrices together to get the new matrix, except in this other representation, right? So I think this is right. I think, okay, obviously this is right. Like, once you rotate a scale, it's not aligned with your coordinate system anymore, right? So you can't do it in 3 numbers. That makes sense to me. Whereas if you had it as a 3 by 3, you can rotate that all you want. Yeah, scaling is a 3 by 1 right now, which actually may not be a good idea. Like, maybe we're destroying animation data in some cases because let's I believe actually we might be storing 3 by 3 in the file. Okay, this is the animation file that we load, and it's a text format, which helps sometimes. Yeah, dude, I'm saving 3 by 3, and it's just always frickin' 1 right now. So actually, because it's literally always 1, if we want to figure out if the rest of this math is working, we can just poke the answer to be 1. Yeah, it's literally always 1 right now. Which means it's a giant waste of CPU to do scale and all of this, but that's fine. We can flag that out later. So here's what we're going to do is we're just going to say, we're going to cheat and say SB is actually 1 because we are advanced and know the answers. And so now How does our old matrix compare to our new? Old matrix. Oh, it's still totally different. What am I doing wrong? Let's print these. Let's print everything. Let's print everything. All right. So old state, blah, new state, blah. Well, let's go back to something that we have a full. Okay, old state, blah, new state, blah. It looks the same. In fact, it doesn't even look like we're more accurate, which maybe gives me a little bit of dismay. But this is supposed to be faster eventually anyway, so whatever. So these look the same to me. Old state and new state now look the same now that we're forcing the scale to be 1. Old matrix and new matrix, however, are not. So what is my deal? I mean, is my whole life a lie here? If I get matrix from it would explain a lot if I get matrix back from this and it's like not the same value that I put in. Let's see what happens. So we set from matrix this matrix, right? And then M2 is a matrix 4, and I'm going to get matrix state into M2, and then I'm going to print matrix M2. Right, all I did was put this into this X form state and pulled it back out. So let's check that. M2, the same. So I must have made a really dumb clerical error. I mean, this is reassuring, like it's not grossly numerically inaccurate, which also means that this isn't going to fix our numerical accuracy problems. They must be potentially caused somewhere else. But well, let's do this. Okay. So we're back here. We do all this. Old state and new state, we're printing them out. They look the same. Old matrix is my matrix, which, oh my God. We were printing the wrong thing all along. It's supposed to be M, not my matrix. I need better variable names. Okay, now they look the same. Now they look the same. Okay. How different do they look if we don't cheat the scale? Probably pretty different. Yeah. So we're going to cheat the scale, and we'll fix that in a minute. Let's comment out these print things. Let's actually just say this. We're going to do this math, and we're going to say state is X, and we're going to comment out this stuff. So we're taking our result of this math and we're using it actually for the animation. And my expectation is it won't actually look any different, but let's see. So we put him in that pose, put him in that. And it is still stretching. inward or shrinking, see? Is it less though? I can't tell. Probably not. I don't think it's any less. Maybe it is. Okay, well, we have eliminated the possibility that this was the source of the error. I guess, that this converting to matrix and back. So we're going to line some things up. Because we're cheating this, we have to say incomplete, stop cheating, scale, use the full 3x3. But we're going to if this out for now. So we're going to say if skip or if do not go to matrix dummy. Then we do this. All right. So we have that for a bit later. Okay. That is good. That's a thing that we can improve. We'll be able to get rid of this and do this as soon as we bring in the 3x3s. But that, I wonder if we had full 3x3s in the witness and I stripped it down for this port because I thought we didn't need it. I don't know. We'll take a look at that. The double less than dereferences a vector. Yeah. How come I'm not using my compile time sparse matrix? Why would you use a sparse matrix for 4x4? Oh, you mean to store these things? Yeah, nah, it's not the right application for that, I don't think. The right application for that would be like a geometric algebra library or something. For this, at least I don't think so, but maybe there's something I'm missing. Oh my God, I've been muted. I've been munching. Anyway, so what I'm saying right now is the shrinking that we're seeing. Let's go back and look at that, right? I was hoping that it just happened to be later in the pipeline, like where we were just looking. But like it happens in the middle of the interpolation, which means it really must have to do with the thing doing the interpolation, right? I would suspect. Like it could be that it just so happens that when you drift further from keyframes, then for whatever reason, things can get more wrong. But if so, we would have expected to see the error in that other place, which we don't. So I think it's here. Who's the artist? Is it the same people from The Witness? One of the same people from The Witness, and then there's others. But everything you see here is temporary. The water is not how the water is going to look. That lily pad is temporary. The brown blocks are temporary. Obviously. The character mesh is closer to final, but not really. So Casey suggested an experiment, which I could try, which is just don't draw the mesh. Just to make it clearer that the bones are actually expanding, but I don't feel like I need that confirmation. I feel like I can see it. So rid of this for now. That's just debug print of the number. We've sort of used that as much as we're going to use it. So let me just do a normalization here, just in case. Undeclared identifier relative state. What? What did I do? I deleted some lines that I didn't want to delete. No, not there. Sokoban. Sokoban. So line 195. Oh yeah, that. Okay. Okay. Still doing it. Still doing it. When I'm drawing my animation HUD, how do I draw the bones? I manually transform. So if there's a problem in the shader with the mesh size, I do not inherit that problem here. Okay, this didn't help. But we know what's coming out of this is valid. So what do we do after that? Well, we call get relative to parent. Let's try this. Well, let's does that help? No, it doesn't help. Look at that. What the hell? Sure looks like this is implemented. I don't know. I don't know what to do except go crazy. Go bananas. I got to go bananas. Okay, I actually know what the problem is. No, I don't know what the problem is. Do I? Don't I? I know what the problem is. And I think we're going to fix it in the morning. But let me tell you what it is. When you store the transforms for a hierarchical structure like this, there's different things you could store. Like one of the things you're seeing here is that, I'm switching back and forth between things that are like relative to the parent node or things that are in the space of the entire object. Those are two representations. Mathematically, you can switch back and forth between them. You might get a little bit of error if you do that too much or something. But as you see here, we don't have error there because if we force a normalize, it doesn't change the output. Okay, here's the thing, is I'm interpolating in the object space, and then I'm converting to relative to parent. Okay? And that is not good because you might have a bone where the bone is not translating at all relative to the parent, but it's rotating, right? And so if you look inside the time step between those two frames, what that looks like in object space is the translation is actually going on a curved path, right? And we're removing that curved path. So we have to go into local space first. And then we have to interpolate, right? So the order of these two things is reversed, is my claim. If you have more bones, is it worse? I mean, I don't really know. It's hard to test that, but yeah. Do people understand? Do you know what I'm saying? Do people get what I'm saying here? Like, you could have some, so the reason to store things in local space also, or interpolate them, is they're a lot simpler, right? If you imagine some bone, right, and like I said, it's not translating at all relative to its parent, but it's like 8 bones down on a whip, right? Then in object space, as the whip moves, its translation coordinates in object space are going to be moving all the time in a weird pattern, right? Even though relative to the parent, its translation is 0 and it's only rotating because it's accumulating the translation of all these bones higher up in the hierarchy, right? And so at some point I screwed up and changed this. It used to be the other way, and I remember changing it because I'm like, oh, it'll be faster this way. No, it's not faster that way. So what we're going to want to do, and I'm going to do this in the morning when I'm fresh, but when we load this file, we're going to make them relative at that time, because we always want to start operating on relative data anyway. So when we load the file, we're going to convert relative to parent, so we don't have to do it every frame. And then we can just get rid of this step. We can do get xform state, and those will just all be in relative to parent space. And this problem, I claim, will go away. Is there any reason not to do everything in local space? Well, so once we're putting animations together, so we definitely blend in local space as well. And then we concatenate them for the output. So yeah, no, we really just do everything in local space. And I think, you know, as I was working on this animation system over time, I was learning, and so I was switching back and forth between various things, just trying to figure out, you know, do certain things save you CPU or whatever. But I think really every operation should happen in local space, right? You know what I'm saying? Yeah, you need object space to actually render it, which is why we concatenate back to object space at the end. But prior to that, we apparently don't need object space at all. So it's a little bit sad because our file format, which I showed a minute ago, this one, these are all in object space. You can tell probably because the translations are all wacky, and that's actually going to introduce a slight amount of error maybe. For some reason, I had the intuition that it would be better to send it in object space, and I don't think that's really true. I don't think that's really true at all. Anyway. This guy has 140 something bones, or 150 something. How many bones? 154. Okay. So, but it's fine because this isn't going to be our final format for shipping the game. We're going to process this into a binary format anyway. And then if we ever go mess with the exporter some more, we can make the exporter export into local space. And then we won't have the tiny amount of extra error that we get from switching, but that won't really be that much anyway. Yeah, so that was that. And I'm happy to have come to this conclusion. If I wasn't really tired tonight, I would just try and do it now because it's really not that much work. But, you know, when you're doing matrix math and stuff, if you just make one mistake, you could spend a lot of time debugging. So I think I will enjoy it and have less trepidation if I do it in the morning when I'm fresh and perky. Yeah, everything local space, I'm pretty sure is the right thing. Yeah. All right, corner piece. See you later, man. All right. Culverfly doesn't quite like the statefulness of scope file and scope export. Well, you could say as an alternative something in front of every single procedure if you want to do that. I don't know. We'll figure that out. All right. Thanks, people, for coming by. We're gonna, in the morning, do another stream and attack this problem. And for now, let's figure out someone to raid. It's not going to be Corner Piece because he just logged out. Wow, there's not a lot of people on programming tonight. FreeBSD ports work. What is this? Oh God, it's like environment variables.
There's the problem.
Lord save me from environment
You know
variables.
what?
Oh my
I
God.
should have known that. Go back, go back.
This is exactly why I'm making this new language, so you don't have to do this
First
kind of
port
thing. Look at all
page
this garbage.
Where SunPoet did this. And I should have looked at his change because, oh, okay.
This guy looks pretty tired too.
Change did that, but
All right, this doesn't look like programming. It looks like wrestling with Unix. So let's look for something else. Zooter development with an eye tracker. See? I don't know if this guy says anything.
Check out this.
Oh, he does. And it's in Python, which isn't as bad as JavaScript.
All right, so we have a bunch of imports that we're missing.
Let's do this. Oh, this is a Zelda Ocarina of Time randomizer. That's a cool thing, right?
So we did merge this and then we, wait, yeah, so we did pull this in.
All right.
It's
Thanks
just
everybody for
that,
coming by, and maybe I'll see some of you
there
tomorrow
was
when we actually go to implement this.
From
See ya.
these files. So the complex are actually probably minor. So if I say merge, it really should be the other way around if you'll let me. Merge